Okay, so today specifically, like I said, you will be setting up boundary value problems. Okay, we are going to be looking for u of xt, where x is a spatial dimension and then t is time. So today we will be setting up two different types of equations. So you're going to read the context of the problem and you're going to set it up. Later what we'll be doing is we'll be solving for u of xt. That's the rest of this unit, is we'll be looking at different types of problems and how you're going to solve for u of xt. Here we will need boundary and initial conditions. There are three main classical equations. First one is k times the second partial of u with respect to x is equal to the first partial of u with respect to t, where k is greater than 0. This is called one-dimensional heat. Second one is a squared times the second partial of u with respect to x. That's equal to second partial of u with respect to t. This is the one-dimensional wave equation. And then the last one is the second partial of u, bless you, with respect to x, bless you. Add the second partial of u with respect to y is equal to 0. And this is called the two-dimensional Laplace's equation. We will only be covering the first two equations, heat and wave. We are not going to do Laplace. Okay, so what I mean by that one-dimensional, there's going to be two independent variables, x and t. One-dimensional refers to the fact, though, that only one of the variables is a spatial variable. So only one variable represents space. So one-dimensional tells us that x is the only spatial variable. Bless you. Or if you looked at Laplace's equation, you would have x, y, and t. Both x and y then would be spatial variables. Okay, so here's what we're going to do for the rest of the notes. We are going to derive the heat equation, we're going to derive the wave equation, and then we're going to talk about what kind of conditions you're going to be setting up, or you're going to need. So we are going to start with the heat equation. Here's the idea with the heat equation. Is the x-axis is going to represent x. And you're going to have a thin rod that goes alongside, that coincides with the x-axis. So it's going to start at 0, and then it's going to end somewhere at L. Okay, so suppose we have a thin circular rod of length L, and it has a cross-sectional area A. The rod coincides with x-axis on the interval 0 to L. So when I'm talking about that cross-sectional area A, I mean this part right here. So that's what your A is. So like we said above in the very beginning, we will be solving for u of xt. So here, u of xt represents the temperature at a point x along the rod at time t. So we'll be able to find the temperature at a certain point along the rod and at a certain time. Now, we have a whole bunch of basic assumptions that need to be true before we can derive this equation. First basic assumption is that the flow of heat within the rod only takes place in the x direction. So flow of heat within rod only takes place in the x direction. So generally the heat is going to be flowing this way, for example, only in the x direction, not in the y direction. Second assumption is that the rod is insulated. So in other words, no heat is going to escape. We will look at a few examples where there is heat escaping, but we're not going to be solving any of those. Next assumption is that no heat is being generated within the rod. Okay, got two more. Next assumption is that the rod is homogeneous. What that means to us is that the mass per unit volume, which is that symbol, it's like a P with a tail on it. Do you guys know what symbol that is? Rho. So rho is going to be constant. The specific heat, that symbol, what's this one? Gamma. So specific heat and thermal conductivity of the rod material are constants. Before we start, or before we continue rather, have you guys looked at this type of problem before in physics? Okay. Oh, this should be interesting then. Okay, we're going to need two laws of heat conduction. First law tells us that the quantity of heat, which we are going to label Q, in an element of mass M is going to be given by the following. Q equals gamma mu, U being the temperature of the element. Second one, we're going to write down the equation, and then I will tell you what this equation means. We have the derivative of Q with respect to T is equal to negative K times A times the derivative of U with respect to X. So here's what this means. Q of T is the rate of heat flow. So overall, this tells us that heat flows in the direction of decreasing temperature. And this should make sense. If this value right here is negative, that means temperature is decreasing. If I multiply it by another negative, it means I'm positive. So that means my heat is flowing in that direction. Yes.
Is that a U sub x?
Yes. Okay. Next thing we need to know is that the mass of a slice of that rod, the mass is going to be equal to rho times A times change in x. So if we look back at the picture we have, I'm going to call this point right here x. Let's say that I'm looking at this slice right here. This is going to be x add delta x. So we're looking for the mass of this slice here. Okay. So then, equation 1 above is going to give us Q equals gamma. M in this case is going to be rho A delta x times U. Star that because we're going to need it later. Next, since heat flows in the positive x direction, what equation 2 shows us is that heat builds up in the slice at the following net rate. It's going to be negative K A U of x at the point xt, subtract negative K A U of x at the point x add delta x, comma, t. What I'm going to do is I'm going to pull out a KA. If I do that, I get U of x evaluated at x add delta x, comma, t. Subtract U of x evaluated at xt. This one goes here. I just reversed them. Okay, next thing we're going to do, of course, is we are going to differentiate that star equation above. We're going to do that because the second equation is Q of T. So if I differentiate this right here with respect to T, I get Q of T equals gamma is a constant, rho is a constant, A is a set value, delta x has nothing to do with T, and then I have U of T. Are we warm in here? Can you just open the door, please? Thank you. Okay, next thing, we need to solve for U of T. If we solve for U of T, we end up with Q of T over gamma rho A delta x. Denominator is going to stay the same, so that's gamma rho A delta x above all of this is q of t, because that comes from the second equation. So that's going to go here. So those a's are going to cancel out. I'm going to write the constants out in front. So this is going to become k over gamma rho. Then we have everything else. We're almost done, I promise. With heat, at least. Okay. Finally, what we're going to do, we're going to take the limit as delta x approaches 0. So, obviously, ideally, you're going to want those slices to be very, very narrow. When we do that, u of t, that is unaffected, so that's k over gamma times rho. What is all of this when I take the limit as delta x approaches 0? Or what does this stuff remind you of? Derivative. Okay, what derivative do we think it is? Does that make sense? That was your next guess?
What's the answer?
Second derivative of u with respect to x. Okay, so then generally what we're going to do is all that's a constant, so we just call it k. So this k is different than that k, but we can just call that entire constant k. So we get k times u of xx equals u of t. Yay! Yep. Isn't that exactly the same as the first equation I gave you?
What?
It is. Wrote it differently, but it's exactly the same. Okay. Now, I'm not going to ask you to derive this equation again. I want you to see it, though, so you know where it came from. You ready to derive the wave equation?
No.
Great, me too. I'm excited also. Okay, so here's the idea with the wave equation. It's going to be set up very similar way. You have the x-axis. The y-axis is actually going to represent u. And what you're going to do is you're going to have a string that is tethered to the x-axis at x equals 0 and at x equals L. So you're going to have some string. So we are going to consider a string like maybe a guitar string that is stretched between x equals 0 and x equals L. Now what's going to happen is the string is going to start to vibrate. And when it does, the string moves perpendicular to the x-axis. So now we said in the very beginning of the notes, and we also said when we got again to heat, that we're looking for u of xt. So in the heat equation, u of xt represented the temperature at a position x and at time t. Here, u of xt is going to denote the vertical displacement of any point measured from the x-axis. So for example, I could choose some point here. U of xt would tell me this displacement at a certain time t. Eventually what we're going to need to do when we get into deriving is we're going to need to look at a portion of the string again. Or like before it was a portion of the rod. Here we're going to call this side x, we're going to call this side x add delta x, and we're going to call that part of the string change in s. So we need that eventually. Okay, as before, we have a whole bunch of assumptions. First assumption is that the string is flexible. Second assumption is that the string is homogeneous. Same definition as it was for heat, that the mass per unit length, again using rho, is a constant. We are going to assume that the displacements, again, which we are calling u, are small in comparison to the length of the string. We are also going to assume that the slope is small. We are going to assume that the tension, which we're going to call big T, acts tangent to the string, and its magnitude is the same at all points. We're going to use big T to represent that magnitude. We got two more. Second to last assumption is that the tension is large compared to gravity. And lastly, there are no other external forces acting on the string.
What do you mean by slope is small?
We're assuming that the string is stretched out enough that we're not going to have a very radical slope on the string. So like it's okay. So before we talk about this, have you guys talked about the wave equation before? There's no v in this equation, so maybe not.
Yeah, that's the wave equation. We didn't have the other one. Yeah. There were waves last year.
There were, okay, so that gives me enough information. There were waves. Okay, so that little portion of the string, we're going to draw that out again. The black part that we call delta S. So it's going to be something like this, let's say. We called this delta S. And we said that one portion of this was x, and then we picked another point later on that we called x add delta x. Okay, we are going to call the right side tension 2. And we're going to need this angle here, which I'm calling theta 2. Here we're going to call this tension 1. And again, we're going to need that angle there. So this little portion here, we're going to treat like a little triangle. Call this tension T, because we said that that's the magnitude of the tension. Let's call this side F maybe. Okay, so if we have small angles, if we have small theta 1, theta 2, then the net vertical force acting on that delta S, on that string, is going to be T sine of theta 2 subtract T sine of theta 1 Okay, so here if I were solving for F, I would use sine. So I would get sine of theta 2 equals F over T. So if I'm looking for the force then, I get T sine of theta 2. So that's where these two come from. Because of this angle where we placed it, here this quantity would end up being negative, which is why we multiply it by a negative to make it positive. Now, here's why we need the slope to be small. If the slope is small, that's what will force those two angles to be small. If these two angles are small, sine then is going to be approximately equal to tangent. This then, if I pull out a t, becomes derivative of u with respect to x, evaluated at x, add delta x comma t, subtract u with respect to x, evaluated at xt. That's another expression for slope. Okay, next thing we need to know is we need to know the mass of the spring. Mass of the spring is going to be that mass constant times delta S. Now we said that the slope is small, so this is going to be approximately rho times delta x, because the string is going to be pretty close to flat. So this is the mass of the string on the interval x, and then x add delta x. Okay, so then Newton's second law is going to give the following. F equals ma. F would be all of this mass we already set up here. A will be the second derivative of u with respect to t. Okay, I want to get this on one side, and I'm going to move the delta x over, and then I'm going to move t over to the other side. As before, we want the portion of the string that we're looking at to be pretty narrow. So we're going to take the limit as delta x approaches 0. If we do that, what does this side become? uxx, so second derivative of u with respect to x. Right side stays the same. That we're going to call a squared. If you call that a squared, you get uxx equals a squared utt, which is exactly the second equation. Okay, that was deriving. Last, what?
There's a lot left.
2.5 pages?
Ooh,
We will be taking notes until the end of the period.
it's taking a toll on my binder.
Okay, good talk. At the beginning of the period, we said we're also going to need boundary and initial conditions. So next we're going to talk about what those boundary and initial conditions are going to look like. Starting with initial conditions. You're going to have certain initial conditions for heat and then certain initial conditions for the wave equation. For heat, the heat equation, you are going to need the initial temperature throughout the rod. So if f of x is the initial temperature distribution, throughout the rod, then u of xt must satisfy u of x0 equals f of x. So this is at time 0, place whatever x is, that will tell us the temperature there. So this is the initial condition if it's a heat equation. You have to tell what the initial either temperature or temperature distribution is for the within the rod. For the wave equation, we must specify the initial displacement, which we're going to call f of x, as well as the initial velocity, which will be g of x. So initial displacement will look the same. U of x0 equals f of x. So at time 0, place x, it'll tell us what the displacement is there. Initial velocity would be the first derivative of u with respect to t. So the partial of u with respect to t at t equals 0 is going to be g of x. So those are the initial conditions. We also need boundary conditions. In the example of the wave equation, we need to tell where the string is secured. So this is going to be u of 0t and u of lt. So at position 0, whatever time is going to be some initial displacement. So in the example I gave you, the string was tethered at both x equals 0 and x equals L. So these would be the boundary conditions then. Okay. Things are going to look different for the heat equation. For the heat equation, there's going to be multiple different ways that you can write the boundary conditions depending on what information you are given. So I'm going to write down a few different examples. first one. Yeah. Thanks. First one could be something like this. U of LT equals U of 0. Okay, so what that tells us is this tells us that the boundary x equals L, so at the furthest most right point of the rod, that end is held at a constant temperature. Could be the same for the left boundary as well. You could have something like this. Partial u with respect to x at x equals L equals 0. So the change in the temperature with respect to position at the rightmost point of the rod is 0. What that tells us is that this boundary is insulated. So there's no heat that will be flowing in and out.
That could be at x equals 0 too.
Yep. Okay, so for the boundary conditions, before I write the third one, just to clarify, you will need one condition at the left side and one condition at the right side. So you may be told that the left-hand side of the rod is held at a constant temperature and that the right-hand side of the rod is insulated. So it could be two different boundaries that you have, but you're going to need one at the left side, one at the right side. And the same for the wave equation. The wave equation, though, is just going to be secured. It's not going to be anything interesting. Last one, partial u with respect to x at x equals L is equal to negative h times u of LT subtract u of m. This is a possible boundary. What this is telling us is that the heat is lost, or heat is lost, by the right-hand side of the rod when it comes in contact with a medium held at a constant temperature. And again, you could have something similar for the left-hand side. After all of that, are you ready to do an example? Okay, here's your example. Consider a rod of length L that coincides with the interval 0 to L on the x-axis. Set up a boundary value problem for the temperature u of xt, knowing the following. First, we know that the left-hand side is held at a temperature u sub 0. Right-hand side is held at u sub 1. And the initial temperature is 0 throughout. Okay, so this is heat. First thing, you're going to have to start out with the heat equation. So that's exactly the equation I gave you on the front page. Okay, we have to define the domain of x and the domain of t. So we know that x is between 0 and L, that we were given above, and we know that time has to be positive. Okay, left-hand side is held at a constant temperature. Left-hand side would be a position of 0. So when x is 0, whatever time it is, temperature is going to be U sub 0. Right-hand side would be when x is L. So that's held at a constant temperature, U of 1. Because t is our variable here, it's a good idea to show that t has to be greater than 0. Your book is going to define the domain for every single line, so that's a good practice. Initial temperature is 0 throughout. Initial temperature means that time is 0. So at time 0, no matter the position, we get an initial temperature of 0. Variable being x, so we need to say that x is between 0 and L. This would be our boundaries. This would be our initial conditions. Or initial condition, there's only one of them. Okay, we got a few more things to write down. This is what your homework is going to be like. So you're just going to read the problem and set up what it would look like. Not too bad? Okay. There are some modifications. When you have internal or external forces, okay, internal or external forces could look something like this. Most of the time, you're not going to have all 4 of those variables. You're going to have 1, maybe 2. G. So example 2 is k, second partial of u with respect to x. Subtract h times the quantity u, subtract u of m.
Blackout.
Did you guys get the 2 equations written down for internal and external forces? Yes. Same thing except instead of u of x, u of t. No, it's not dead, but I can't turn it back on right now. Okay, example 2. Okay, what this part tells us is that there's heat being lost. There's heat transfer. This tells us that there's heat transfer. From the lateral surface of the rod into a surrounding medium held at a constant temperature U sub m.